Hello, everyone. My name is Joseph Townsend, and this is my Physics 2211 Lab 4 on oscillations. For my introduction, the overview of this lab was to predict the motion of a spring mass system and to demonstrate its differences from simulations compared to a real-world example. The methods in this case used were computer simulations, in particular WebP and the results, or the simpler results, were that the energy principle was satisfied as the total energy change remained zero. As for principles utilized in this lab, there were Newton's second law in the form of velocity and position updates, and the energy principle. Going a bit deeper into fundamental principles, I highlighted the equations that were used. As I've said, we had velocity and position update formulas, as well as the energy principle, in this case, in terms of change in kinetic, change in gravitational potential, and change in spring potential energies, which through our assumptions all summed up to zero because there were no surrounding work involved. Additionally, there was also Newton's second law with the F net, or with the net force equaling the spring and gravitational forces. For our initial conditions, since we utilized the givens from pre-lecture video 52, we have been told that the object's mass was 0.402 kilograms. In tracker, after aligning the axes in the same way that the pre-lecture video had instructed us to, I had received an initial position of negative 0.118 and negative 0.647 meters. The initial velocity was, of course, zero because the spring was at rest. And then the gravitational constant, of course, was 9.8 meters per second squared. And the spring constant, as well as the initial fixed length or initial relaxed length of the spring, was separately 6.83 newtons and 0.123 meters. After going through the tracker software, I was also able to find the oscillations in the X and the Y direction as seen on the pictures below. For the code, after plugging in the given initial conditions as well as the formulas for the initial conditions, which were the basic kinetic and potential energy as well as total energy formulas, followed by the spring formulas to find the extended lengths of the spring, these values were inputted into the while loop with time less than 10.5 seconds. And essentially, the kinetic energies, or the changing kinetic energies, was constantly updated and then graphed onto WebVPython in the simulation. For the results and errors, one specific error could, of course, be the tracking point mass in the tracker software, because all of this were done by hand and there were over 100 frames. There could definitely have been some deviations in terms of how accurate the center of mass was per frame, as well as an assumption that there were no surrounding energy at all acting on the spring mass system in the video. As we know, drag and air resistance is definitely a thing in the real world, but since we assumed that that was zero, or essentially that the spring mass system acted in a vacuum, that might be a main cause of why the simulation deviated from the actual model in terms of its periods or in terms of its oscillation times. Is the energy principle satisfied for our first what-if question? I would say yes. As we looked at the first graph in the WebPython software, delta E, or the change in total energy, remained almost exactly at zero. Since we know that, or since we assumed that there were no work done by the surroundings, the total energy needed to be zero in the system. And as we could see in the graph, that is true, as the change in kinetic, gravitational potential, and gravitational potential and spring potential energy all summed up to zero and change in total energy. As for the comparisons of periods, I took the first 3 periods of both the X and Y direction and averaged them out to have a more accurate value. And as we can see, the period times were different in the X and Y direction. One of the biggest impacts in this case would be the fact that the spring constant is derived from the period, and an uneven spring constant in the X and Y direction would mean that there would be a lot of deviations in the calculated spring force. That's the end of my presentation. Thank you very much.